Welcome to everyone from across the United States and Panama, and welcome to all of you in the room. This is a workshop to illustrate application of a tandem evolutionary algorithm that was coded up, written, created by John here and back in 2020. John is a former student of one of our instructors, Donna Rizzo, here at UVM, and coded this up in MATLAB originally. And with funding from the Critical Zone project, we have ported that code base from MATLAB into Python, and with assistance from Transcend Engineering here in Vermont to do that. Today, what we'd like to do is just illustrate how TEVA can be used and applied in environmental data sets. This is a 3-hour workshop. We've split it up into 3 chunks separated by long breaks so that we all can stretch and move around a little bit and ask questions and work independently. I'd also like to acknowledge the Water Resources Institute that has hosted our space here today and our online presence. And thank you to Hannah Fisher, who's our communications person in the WRI. And there they are, there's your logos. The other entity I'd like to acknowledge is Quasi. Abner Bogan is online, and joining us at around 2 o'clock will be Clara Cogswell. They're here to help you with any computing issues that you have, and they have really done some excellent work to get us ready for today to host this. Here are your instructors. I'm Kristen Underwood, a research faculty member here at UVM in the Department of Environmental Engineering. Donna is also here. John Hanley, as I mentioned, the original creator of the code, is joining us from his new position at Special Olympics. And then we have 4 PhD students that are helping us instruct today: Ali Dadka, Ryan Vanderheiden, Kaylin Gramling, and Sharya Swami is online. Ryan is feeling a little under the weather, so you'll see a lot of the products of his work in the last couple of weeks here, but unfortunately, I don't think he's going to be able to join us today.
So we'll take credit.
So we'll take credit for all his good stuff. And as I mentioned, Abner and Clara are making it possible for us to be with you today. Here's a quick workshop overview. Again, these are chunks, 1-hour chunks, roughly separated by 15-minute breaks, really 45-minute chunks separated by breaks. We'll give you an overview of TEVA and its capabilities in session A. Then in session B, we're actually going to run TEVA, and you'll be able to run it as well on your laptop. And then the third and final session, C, will be on interpreting some of the TEVA output. So broadly, our objective today is just to showcase TEVA and let you see how it can be so broadly applicable to environmental data sets, but not only environmental data sets. So if you work in other domains, or if you have colleagues who work in other domains, medicine, language, disease transmission. There are numerous applications of this tool. So we're just limited by our imagination. After completing this workshop today, you should be able to know how you need to pre-process your data sets to run through TEVA. You'll be able to operate TEVA using the Jupyter Notebook and the Quasi Jupyter Hub setup. And you'll be able to access and visualize TEVA output and then interpret it. I would say that, speaking from experience and from Donna's and John's tutelage, it can take several weeks to months to years to really know all of the nuances of this tool. But we're prepared to work with you in your data sets if you want to. Ali, you had a question.
Yeah, sorry to interrupt you. I just got a text from Sherry that says people online cannot talk, so we cannot hear them here. Do you know if that's
Well, I think for the moment, if you have feedback or questions, you want to type them into the chat. So we may work on the ability to have those of you who are joining us online actually talk such that we can hear you here in the room in UVM. But we might have to do that, troubleshoot that at a break.
I can just turn on my volume and see if. I know I can't hear you.
I'm probably gonna get feedback. Yeah.
Because there's no actual like speaker hooked up to
Yeah, gotcha. So unfortunately, we will have to take your feedback, those of you who are joining us online, through the chat for the time being.
We could at the break mute this and then use one of the laptops here in the room to hear them.
That's a great plan. So hopefully you heard that plan from Donna. During the 15-minute breaks, what we'll end up doing is muting the podium and then turning on the speaker of one of our laptops so that we can hear your questions or comments here live at UVM. But we'll probably reserve that kind of active exchange for those 15-minute break times. Thanks for your patience as we work through these. Thank you, Sharia, for posting that note. Okay, you'll probably hear me bounce back and forth between Eva and Ava because I grew up pronouncing these sandals TEVAs. And then when we decided to abbreviate the tandem evolutionary algorithm as TEVA, I learned that most people pronounce them TEVA. So I'm probably gonna bounce back and forth. Both, either are equally acceptable. And we've heard, there's a rumor that there's a geographic disposition for how it's pronounced, but we'll see.
And
yeah,
I wasn't the one to come up with the acronym. Somebody else was. And I thought it was brilliant because John wore Tevas every day, including 3 feet of snow.
Okay.
I'm joking a little bit.
There you go. That's awesome. Very appropriate then.
Oh.
Chacos, actually, John says. Okay. Good. Okay. So you've all seen this slide, I think, in the promotional materials for this workshop. We're excited about it because it's a new and novel exploratory data analysis tool that evolves combinations of features that can drive outcomes, not just singular features, but combinations of those features. And in the complex systems like the critical zone that we deal with in the environmental fields, this tool is capable of detecting conditions of equifinality and feature interactions. And these are both phenomena that characterize complex systems quite a lot. And we're going to define those in just a few minutes. It's applicable to both spatial and temporal data sets, which of course we work with all the time in Earth systems. So that's about a bonus. And as I mentioned already, it's now been migrated to open access Python, and we're hoping that therefore it will be more used. And we already have noticed some downloads in the few days that we've made this HydroShare resource public. This paper was circulated to all of you ahead of time, and I suggested a couple sections at least to read from this paper as background material for today, because it will just help reinforce some of the terminology that we're going to be using and batting back and forth. In this paper, we introduced the environmental and ecological fields to the use of TEVA. And again, there are other papers out there that have applied TEVA in the engineering fields and the medical fields and the field of disease transmission. So if you get really excited about TEVA, we can share those other papers with you just so you can see how those tools have been applied. If you're joining us today, you already hopefully have signed up for a HydroShare account, because without a HydroShare account, you will not be able to use the resources we're sharing with you today. What we're going to do now shortly is have all of you do a second step, which is request access to Quasi Jupyter Hub. And the reason we're gonna have you do that now is that there's a little bit of time that it takes for Quasi to approve of your request to access Quasi Jupyter Hub. And so we thought that that approval process can be happening in this first 45 minutes while we share the slides. So I think we can do this without leaving the slides. But if you would all avail yourselves of the HydroShare resource link that was provided in yesterday's email, click on it to go to the publicly shared HydroShare resource for this workshop. And I'll give you just a couple minutes to do that. And in the chat, put any questions that you might have or problems that might arise. But click on the HydroShare resource link. It was provided in yesterday's email to access HydroShare. And there's the
Kaylin,
link in the chat
Yeah.
from Kaylin as well, in
Thank
case
you.
you lost track of that. And we're just gonna
wait,
sing the Jeopardy song while you do that. And for those of you who have never accessed a HydroShare resource before or used Quasi Jupyter Hub for your computing needs, there's going to be a message that'll pop up asking you to request access to Quasi Jupyter Hub. So if you're in the HydroShare resource now in this moment, look to the upper right corner and there's a link to connect to Quasi Jupyter Hub. There's also, by the way, a README
This,
file
where it says open with,
share resource
sorry.
that gives you pictures and instructions for doing exactly what I'm trying to describe for you to do in words.
Python, choose Python.
Choose Python.
Server.
And yes, we mean the button that says open with.
The README documents in the chat as well.
Sharia put the README document in the chat as well. Thank you, Sharia. Give this just a minute and then I'll ask if everyone's ready to go.
Well, how are we doing here? Everybody ready here? Thumbs up?
My server's starting, but
Yeah, it's gonna, that's why we're having you.
Did any of you get the message saying request access? And when you do get a message requesting access, we're asking for you to put a little comment in there that just says, Abner, we're in the TEVA workshop requesting access. Because when all these requests for access file into Abner's box, he needs to be able to know that we're real people making this request and that we're not bots. So that's helpful if you just add a little comment when you request access.
That's what's good about having people in the room, because if they can do it, then I'm assuming
Yeah.
folks online were successful.
How about anyone here not able to successfully access just yet?
Kaylin, can you see everybody's screens?
Has everyone made a,
Oh, in front of me?
Yeah.
Screen's looking good.
Okay.
please tell which file to open with Jupyter. There are 3.
we're not opening those
Not
yet.
yet. We just
We're
wanted
just-
access.
Simply just getting you access.
If you open the README file, there's a couple of steps instructions
Yeah,
there.
that's why the README file's there. So there's a couple of steps to process it. Should be simple, but you don't have to do that yet.
Right. we're just doing this now so that anyone who has not previously had access to Quasi Jupyter Hub can make the formal request, and then Abner can approve that request to give you access today in the workshop. Any questions about that? Does that make sense?
Good, that's what we were hoping. Don't you love it when a plan comes together?
For sure. Caitlin, is there any chatter that where folks are having issues?
There's
Looks
little
good.
hearts in the thing.
All little hearts? Okay, sweet. Okay, I'm gonna move on unless I hear otherwise. Okay. So we are now successfully in workshop session A with introduction to TEVA, its capabilities and its advantages. And in this first couple of slides, we'll just talk about the motivation for TEVA, why it was created in the first place, and I'll invite John to chime in through the chat, and Donna certainly to chime in here from the room. This is a non-parametric method that's different and has some advantages over logistic regression and random forest.
And we were hoping John would be able to do a couple of these slides, but given that he can't even voice himself here, I think
Right.
we're gonna have to take over.
We're gonna have to hear from John within the break times, I think, yeah. TEVA is really useful for data sets where we know the outcome category or the classification. We can use it on both categorical and numerical data sets, though, if we pre-process our continuous data into clusters or categories, or bin nodes. The really cool thing about TEVA is that not only does it identify the features that are important in driving a particular outcome class, but also the specific value ranges of those features. So we might know that snow depth is important, but actually a particular outcome class might be associated with snow depth between 25 and 47 feet, for example. TEVA may tell us that. We can also detect interactions between features using TEVA, and that equifinality condition where we have different combinations of features that are associated with the same outcome. So an example of that might be, we have an extreme flood that results from steep slopes and intense rainfall on soils that have high antecedent moisture. That would be an example of 3 features collectively that are associated with an extreme rainfall event. On the other hand, in another situation or in another season, we might have an extreme rainfall result from deep snowpack and warm temperatures. And so that's an example of equifinality, where we have different combinations of features that are linked to the same outcome. And we see this kind of phenomenon repeated liberally throughout complex systems.
And so we've had a lot of reviewers think that it's like a logistic regression method, because that's what logistic regression is kind of good at doing, but it's not. The only thing I want to emphasize here is that there's no p-value associated with this. If those of you who want to learn more about this, there's an objective function for this that we are going to talk about that gets at a probability, but it is not a p-value associated with a given outcome. So you're going to have to let go of any kind of statistical method that you've known before that does what this does. And I know a lot of people use random forest, right, for feature selection, which is really kind of what this algorithm was designed to do. But it goes beyond that, because with random forest, although it's robust, your end result still starts with one leaf of a tree and then creates, and that guides the whole answer that you're going to get later on. That's not what this method is doing either. So we think there's huge advantages. we wanted to write better than logistic regression and better than random forest, but we're just gonna say it's different, okay? All right,
Another great advantage to the tool is it's really robust to varying input data types. So you can have categorical, numerical, continuous data, and those data sets can be skewed in their distributions. They may even have missing values, and this tool is all very robust to that. And it's also robust to having target classes that are unequal in their number of observations.
so you know how that can cause a problem in a lot of statistical methods, you have to have balanced data sets. This was kind of designed for looking for that. Like, I don't know.
I think as engineers and as hydrologists and environmental scientists, we're constantly dealing with data sets that are imbalanced, right?
Yeah.
For sure. Just because nature is that way.
And so just to emphasize, all of the input features can be any kind of variable. It's the output feature that has the constraints in this particular case. It has to be a cluster or a classified value that you put in this very last column that you're trying to map something to.
Okay. So just a few quick slides on terminology. And for this, I'm gonna tag team a little bit with Kaylin. Hopefully you've been introduced to these terms if you read the paper ahead of time, but you're gonna hear us talk a lot about CCs and DCs, or CCs and DNFs. These are conjunctive clauses and disjunctive normal form clauses, or for short, disjunctive clauses. And in the example I just gave, a conjunctive clause would be steep slopes, high antecedent soil moisture, and intense rainfall. 3 features connected by an and operator. That would be an example of a third order conjunctive clause because it has 3 features comprising it. DNFs are combinations of CCs. So in the case of an extreme rainfall event, we might have a DNF identified by TEVA of that example I just gave. On the one hand, a third order conjunctive clause of steep slopes, high antecedent moisture, and intense rainfall, or on the other hand, a second order conjunctive clause of deep snowpack and warm temperatures. And either combination of CCs may result in the same outcome class, which is an extreme rainfall event. So TEVA, the tool, evolves, because it's an evolutionary algorithm, it evolves solutions of CCs and DCs in 2 passes. The first run of TEVA is for a conjunctive clause evolutionary algorithm. We pass the CCs that are evolved from that into the tool again to get a disjunctive normal form outcome. And so that's why we call it a tandem evolutionary algorithm. We're running it in 2 passes. The first pass to get the CCs, the second pass to get the DCs. And we'll actually see this output when we run the tool in the next session. I'm using the term features because that's what we usually call things in the data science, machine learning, or computer science fields. Statistics folks might be more familiar with the term factors. Same difference, features are factors. In our paper, we had to use factors because one of the reviewers was a statistician and made us change all of our features to factors. So that's what you might see as you read through the paper. Feature interactions or factor interactions are identified in the outcome of the CCEA, the conjunctive clause evolutionary algorithm. And that you should be familiar with what feature interactions are. That's when the effect of one feature is dependent on the value of another feature or features. And essentially in that case, prediction is more than the sum of the individual feature effects. As a side note, in the health and computer science domains, this is sometimes called epistasis. So you might see that word floating around other papers. And again, we've talked about equifinality These are identified by the DNFs or the disjunctive clauses that come out of the second pass of TEVA. Another term for equifinality used in the computer science domain is heterogeneity. So you might see this in some of the papers that we link to. Okay, I'm going to stop here and let Kaylin describe for you. We've been talking about an evolutionary algorithm. What the heck is that, and why is it important?
So I'm going to give it's going to be a very brief and very high level overview of evolutionary computation and how that links into the CCEA and the DNFs that we just talked about. So you start with a usually randomly initialized population where an individual is some genome. Sorry. From that population, you have a random-ish selection of parents. You can bias it towards fitness level. So kind of fitter parents are more likely to procreate. Those parents then create children using, in this particular algorithm, there's both crossover and permutation. Crossover, you take the two parents' genomes, you combine them together in some certain way to create a new genome. Permutation, you randomly flip bits. So it's mutation. I think permutation happens in, is it 50%? It's a 50% probability.
We have a pretty high.
There's a high probability of
Yeah.
permutation.
Which is not the norm in a lot of evolutionary algorithms. So those individual slots that you're putting your features or factors into, those are getting randomly swapped out for something different to keep a lot of diversity in this.
And then you have a fitness function. This is the hypergeometric probability fitness function used in this one, which I don't have enough of an understanding to explain.
Anybody else is welcome.
And then the children are the next generation of our population. There's an archive here where we're keeping the best fit individuals. So that's what's going on with these genomes. Our genome here is both a feature mask and a feature range for the first phase. It's a tandem evolutionary algorithm, so there are two different evolutionary algorithms joined together. The first one is the conjunctive clause, where we have the feature mask, whether or not each feature is included in the solution. The features are down here: soil depth, snow fraction, mean slips. These are examples I pulled out of the paper. If a feature is included in the solution, there's a range that's associated with those values that are included. And so those are evolving as along with the feature mask. So the conjunctive clause, a little bit more in depth. This is the first evolutionary algorithm that's being used. It's a combination of features joined by the word and that may or may not be correlated and somehow interact to create that outcome. Here we have snow fraction and mean elevation and mean daily precipitation. The order is the number of features that are included in the solution. So this would be a third order clause. If this was 0, it would be a second order clause with just snow fraction and mean elevation. These clauses are then taken into the next phase. So the next algorithm, which is the disjunctive clauses, otherwise known as the DNF, disjunctive normal form, where the mask is whether or not a particular conjunctive clause is included in the combined solution. So we have our conjunctive clause number 1, 2, 3, 4, 5. And whether or not that one is included. So we have 2, 4, and 5 here. Those pulled out are these clauses of evolved conjunctive clauses. So this one would be snow fraction and mean elevation and mean daily precipitation. So this, that one, and that one with those associated ranges, or this solution, which is soil depth and snow fraction with those evolved ranges.
Yeah, it's a question, 2 questions.
No, you go first.
Okay, yeah, just real quick.
I went through it fast.
No, it's fine. Just on this slide.
Yes.
So the feature ranges for snow fraction are the same in both, but does that have to be the case, or can they be
No, that
different?
was just me copying and pasting.
Oh, okay,
Yeah.
but they can be different. Okay.
Yeah, they can be, they will most likely be different. Unless there's a very specific range that this is picking up on.
But like Kristen's example was perfect, because in one situation, there might have been no snow. And in the second situation, it was deep snow with warm temperatures that caused the issue, so.
Yes.
So if you weren't running this in tandem, then this part of the algorithm would only pick up like individual ors versus like being able to have those and
Yes.
interactions?
Theoretically, yes, but that's not the way the
Right.
program's written. You could go in eventually and change it.
Okay, I'm just curious, so like this section also couldn't come up with its own and combinations.
Correct.
That are then, okay, so this is like really to get kind of.
So this is where the equifinality
Yeah.
comes in, because you're able to have different types of solutions to reach the outcome. Yeah.
And we're actually hoping for the latter, because we think that's where this algorithm outperforms other existing methods.
Yeah.
If it truly was just one set of this and this and this and this, you should probably use random forest, way easier, quicker to use. So, yeah.
I have a quick question, maybe this is related, but like, how do you limit order? You know, cause there's some case where you could get like.
Wait for the break.
Okay.
Yeah,
That's
that'll
gonna be a
be,
great question to have.
you'll see cases of that as we run the tool, and Ali will be talking about how to
Help with that.
consider
That's
those.
exactly why this becomes a dangerous tool to use. Not dangerous, just interesting.
Thank you, Kaylin. That was a great brief description of evolutionary algorithms.
We
Kaylin
offer
just finished.
classes.
Yeah, Kaylin just
What?
finished a semester-long class in evolutionary algorithms, so that was your introduction to the topic. If you want to take your own class, yeah. Okay, I just want to talk real briefly about how we're going to pre-process data for running the tool. And I'll describe the data set that we have shared for you today on the HydroShare resource. As we mentioned, we can have target values, our outcome values that are continuous. It's just that we need to bin them into classes or bins before we can apply the tool. And the number and the value ranges of your bins for your target variable will depend on your domain and the research questions that you're asking. For example, in the data set that we're going to use today, I ended up, my target value was stream dissolved organic carbon. And from a number of observations, I simply used Jenks natural breaks to divide those into 2 classes, and in another case into 3 classes. You can experiment with a number of bins as your outcome classes as well, depending on your application.
Yeah, luckily, a lot of the medical data sets we've done will been like
Cancer, no cancer,
or cancer, no cancer, yeah, depression or various
no
degrees of depression, yeah.
Okay. Again, TEVA can handle a range of data types. We need to bin them. It can deal with missing data. It's robust to outliers. So here on the right is just an example of how, for example, you could take categorical data from the CAMELS data set and just create a nominal number to handle that if you wanted to use those for outcome class.
Be a little cautious on the missing data. It's robust in the sense that you can have missing data, but if you have a couple of observations where a lot of the data are missing, you might want to just drop those observations. So
yeah,
it's forgiving. We've had examples up to 30–40% of the data can be missing, but don't go overboard. You've got something that's got 80% of the data missing in all those columns, just drop it. It's not helping your situation.
Yeah, cool. All right, so we've reached the end of session A. We're gonna take a 15-minute break and start session B right at 2 p.m. Eastern time. But in this time period, you're welcome to put your questions in the chat, to converse with Abner if you're having difficulties connecting to the HydroShare resource. And we will mute the podium and then enabling you to speak your questions into Zoom if you'd like as well into our room here at UVM. Any questions or concerns in the moment?
You see any hands raised? Maybe have them raise hands.
Yeah, raise
first,
hands if you have.
and then we'll mute if needed. Oh, we have a question
We have a
live.
question in the UVM office. Okay.
Question, when it gives you those ranges in the output, are those limited by the values of your data that you put in, or through the evolution, can that possibly change at all?
It is limited by the data set that you supply it. And so there's two ways there's value ranges associated with the bins that you might want to take your continuous variable target data and bin those into classes for outcomes. But I just want to make sure that folks are aware that that's distinct from value ranges of the input variables or features that will be evolved by the tool when we run it, if that makes sense.
Yeah.
Yeah. And when TEVA evolves value ranges, those value ranges for the input features will need to be within the bounds of what was supplied to it, essentially. Good question. Yes, Alexander.
I'm curious, so if we assume that missing data isn't really an issue, do you all have any guidelines on how much data you need to use an algorithm like this algorithm?
Oh, yeah.
Like, what do you mean? You're worried about too much or too little?
Too little in particular,
little.
yeah.
It's designed for big data,
Yeah.
but we've run it on
Smallish data sets.
data sets.
I mean,
yeah,
the
I'm the
example
same.
we're gonna run today, for example, is 91 observations and 54 features. So that's small in terms of big data, and it runs super fine and fast on that. Our colleagues at Transcend Engineering have been running this tool using tens of thousands of observations.
satellite
and it handles
imagery,
it.
so huge.
So it works, okay, so it's kind of this, maybe the same sort of guidelines in general, just more data, better.
More data better, but it's useful. It's useful for smaller data sets where you do expect these phenomenon of equifinality and feature interactions, and it would be better than random forest or logistic regression in those cases.
Which is why for environmental applications, it wasn't what it was designed for, but I think it's cool because most of the interesting environmental problems, like why do we have blooms in Lake Champlain? It's expensive to collect a lot of data, but at the same time, the reason we don't know the answers is because it's a really complex issue. So it's probably not something that's going to be easily explained by like logistic regression or regression in general.
Great, thank you.
Jess, you had a question?
Yeah, kind of going off of that, so 91 observations for 54 features would be, like, that's a lot of features for the number of observations. So if you run up against like sort of like an overfitting problem, potentially, of like having too many features for the
That
observations.
we're going to talk about in how the data get displayed.
Okay,
You're going to want to bias, you're going to see that there's a lot of good solutions that are provided to you, but some of them are likely overfit.
Okay.
And so we're going to walk through how to tease out, not looking at those first.
in order is gonna be helpful.
Order
So
of
order
your,
of the solution.
you want low order, you want to look at your low order solutions first.
Yeah, Caleb.
There's a chat question.
Okay.
It seems like there are some parallels with k-means clustering in that the algorithm defines or identifies high dimensional patterns that group observations together. Is that a fair comparison?
Again, because it's,
Sorry, I just added an answer.
Oh,
what happened?
Sorry, I put an answer in the chat.
Okay.
okay. I will say I just put in a big proposal today, so I'm working on limited bandwidth, and I sort of
That's why I'm trying to help
skipped
her
out when
out.
you had that question.
Shari said, I didn't see what Shari said. Maybe read its answer, but
Can you?
That's a great observation. TEVA and k-means both find patterns in high dimensional data, but TEVA goes further. While k-means clusters observations based on proximity and feature space, TEVA uncovers feature interactions and equifinality, showing how different combinations of feature, it just shifted. How different combinations of factors can lead to the same outcome. It makes TEVA more suited for analyzing complexes with predefined outcome classes, while k-means is more exploratory and assumes simpler relationships.
exactly. That's beautifully typed and described.
Well
Thank you,
spoken.
Sharia.
Thank you, Sharia.
Because I don't want to go into the interactions too much.
Yeah.
But k-means, right, probably the most famous classifier out there. But it is still taking a bunch of features and usually looking at some sort of distance. You can describe that distance in various ways, but that's not what this algorithm is doing.
And John Hanley spoke into the chat, good answer, and he would also add that TEVA provides feature selection on top of that.
Yeah.
So
I use it most of the time for feature selection first. Then worry about how it maps to different classes in a day. If your problem is spatial and temporal.
And just like many other tools, like random forest, it's an iterative tool. You can apply it in order to, maybe in that case of 54 attributes, you might run it first and see that maybe half those features were not even archived by the algorithm, and therefore you could eliminate them the next time you run the tool. So it can be a very iterative
And those of you who know
process.
more about clustering methods, we didn't give them John's original paper, did we?
We did not.
But
We
it
can
was
make it
tested
available.
on, the clustering algorithms that are put out there by the computer science community, some of which we think are kind of dumb, but it was tested on a whole slew of those to see how it did on different types of clustering.
The main paper is like tandem evolutionary algorithm for identifying causal rules.
Mhm.
All complex.
Yeah. We just didn't want to give the group that paper yet.
It's for the super interested folks because it's got some terminology that's a little hard to wade through, but I thought it was a very cool paper and application. Other questions or comments online or in the room? Pardon?
Thanks. So when we move to the next session, we will talk about selecting the mutation, permutation rates and order, or is that set?
You can change it. We're gonna suggest, given that we've played around with that so much, that you use the defaults that are set there, but by all means, one of the reasons we wanted it to be open source Python is so that people could go in and change that if they wanted to.
Okay. And what about the fitness threshold? Is that?
The fitness threshold isn't as big a deal, and you're gonna see why when you see how this thing displays solutions.
Okay.
Madison?
So when you're using this for feature selection, and you have kind of you have equifinality, like you have multiple combinations of features that could lead to one outcome. I mean, I guess you could say it depends, but how do you kind of parse out like which set of features to use? Like say you're using this for feature selection to train another machine learning algorithm, and you have multiple solutions that could lead to that. How do you kind of think about which features to use? Because with random forest, it's like, here are the top 50 most important features, and they rank them out and they give you feature importance. But this, it gets into the interactions, so like it makes it more
And it's
tricky.
Yeah, that's a great question, and it's why this should be used by people who understand the underlying problem and could have a logical explanation. That you're gonna see, given how low some of these probabilities are, and this is why if I explain the fitness function at some point, it starts with given this many houses that are infested, or given that you surveyed first this many houses and this many are infested, what is the probability that you would see a pattern of this and it matches this outcome? And sometimes the probabilities are so low that as long as it's not overfit, that's a really good answer. It's kind of up to you to explain why that set of combinations is linked to that, but it would be highly improbable that wasn't a meaningful solution.
And just like all the many tools, random forest included, you need that domain expertise to kind of feed back into the interpretation. And you just described that in whatever paper you're gonna produce, as well, I think.
And if you don't see the obvious answer in the set of solutions, like there's always one that, oh, yeah, we know high nitrogen and high phosphorus produce blooms in Lake Champlain.
Mhm.
If you don't see that in your solution set, I call that the duh answer,
Mhm.
then you know you ran it wrong.